The first talk is by Emil is giving this talk on metaprogramming with ML modules in MIRAGE.
Thank you very much. Phew, I just got it all working about 20 seconds ago, so I'm actually out of schedule. I'm only doing this at the beginning of the talk. So, a bit of context. I was here 4 years ago, and Thomas Gazinier, who is sitting over there, and I were very optimistically at the ML workshop talking about a new OCaml operating system. And since then, it's kind of been a bit of a roller coaster ride. We've rebuilt the entire operating system about 3 times. We've not given up. We're still going. And we had to write a whole package manager to help manage the amount of code that came out of it, the OPAM manager. We managed to find real users, so we've actually had quite a lot of feedback into how to build these operating systems. And at the same time, I wanted to talk to you about the effort that has been most significant from an ML design perspective. We've functorized the entire universe of operating system dependencies and actually made it usable as well. So, well, more usable than it used to be. So, just to give you a sense of the project goal, how many people have heard of MirageOS? How many people have seen the previous talks? Whoa, okay, I must go home. So I won't dwell too long on what Mirage is, but our essential goal is that we want to write quite portable application logic and also make sure that it can be deployed into very exotic environments. And these environments range from obviously from Unix binaries to also to standalone Zen kernels that have no OS dependencies, and also even JavaScript blobs. And so this presentation can be compiled into lots and lots of different modes, and it's all done by assembling lots of policy together as a series of functors. So the key question is, how do we express all of these combinations without OS dependencies creeping through our code base in the way that it normally does in these kind of code bases? So these slides are, as of 30 seconds ago, being hosted in MirageOS 2.0, which is running on this little ARM device. It's about a 1 megabyte unikernel, and I will just prove it to you by, well, this is the very raw console. This is running on a virtual machine, so the fonts are a bit messed up, but here we have Zen running on an ARM, and the DEX is a virtual machine. It's got 256 megabytes of RAM, but it can run on about 12 megabytes. I just thought I'd play it safe for this presentation. And the binaries themselves are small enough to track in Git themselves, because the entire standalone operating system is so small. So what does this look like from an ML perspective when you actually write this code? So everything in MirageOS, down to the Zen device drivers, is written in OCaml. And so we clearly need a way to structure our code such that we can describe what it means to be a different operating system or a different device driver or a different network stack. So what we have are 3 things. We have a collection of module types, and these describe structure or parts of an operating system, such as a device driver. I'll give you some examples. Then we have a collection of independent libraries, independent of the module types, that often satisfy the signatures if they want to type check. And they implement the actual module types using a number of different mechanisms. And only libraries the application needs are ever linked in. So we don't really have an operating system. We have a collection of libraries that, when linked together, form an executable operating system. And to model dependencies between these libraries and components, for instance, a web server like this is quite complicated. It's got some storage, it's got some networking, it's got some HTTP logic, and we use functors to model dependencies between these things. So there's one key insight that we had quite early on, which is that forcing people to functorize all of the code they write is very painful. It's a very heavyweight operation that tends to lead to either insanity or people not using your project. Because it's a separate module language that is, as Andreas pointed out this morning as well, isn't quite as expressive and as user-friendly as the core OCaml language. So what we do in Mirage is that we provide an EDSL that, in very much the same spirit as Andreas' 1ML talk this morning, embeds the module and functor language into the host OCaml language, where they can be manipulated more easily. And then in turn, in order to evaluate the modules that we come up with, we then use metaprogramming to evaluate the result into a series of concrete modules that then form an executable operating system. So we functorize everything. We then provide an EDSL to describe how to apply the functors, and then we go back into OCaml code afterwards to end up with a real executable. And I'll show you examples of how that works. So the reason for doing this, the reason for all this functorization, is because this one workflow that is the magical workflow that we've been looking for years that makes it easy to develop day-to-day code using this stuff for users. So what we all we have to do to build these websites is that I have to, first of all, write my OCaml application using some Mirage module types. I'll show you those. And then we just run this front-end tool that just says configure it for Unix. We then we debug everything under Unix using our normal operating system. So we cd an application, we check our dependencies, we make a build, the usual kind of stuff. Once it's debugged, though, all we have to do now, because we've functorized our OS dependencies, is just to generate a new interpretation of our main function under Zen, make the build, and everything else just kind of works out. So I'm going to go into a bit more detail now about how this actually happens behind the scenes. So the first thing I said that we have a collection of module types, and this has been an interesting exercise in using the OCaml module system to define a lot of aspects of operating systems that you might not otherwise think about. So here's the first example of a device. And a device in a normal operating system is a device driver, for example. And it's something that typically has an identification, it's got some I/O mechanism under the hood, so we have an alpha I/O monad, and you can't do much with the device beyond connect and disconnect it. But this device pattern is obviously something that is permeated all the way throughout the low-level bits of the stack. But in Mirage, we can also use this for very, very high-level constructs. So in addition to building a low-level network device, I can build an HTTP REST device, as long as it satisfies this one signature, and we don't really care exactly how it's implemented. So this is a very simple use of module types to define device drivers. Then we have flows. Another thing, obviously, very useful in operating systems that do something is the notion of a network flow. And here we've created something slightly more abstract. We've said that given the existence of some buffer type and the existence of some a flow endpoint, we're just defining mechanisms to read, write, and write a collection of buffers to these endpoints. And notice also we're just using polymorphic variants there to just record exactly what the results are. So we're instead of raising a number of exceptions for the common path, for common errors such as end of file and so on, we just raise explicit errors. For anything else, we raise exceptions. So we actually try to use polymorphic variants the whole thing, but without full row polymorphism, it's very difficult because we can't extend the error types easily with pattern matching and so on. So we still use exceptions in our interfaces, but we're trying to reduce their use of them as much as possible and hopefully use open types in the future. So then the composition becomes a bit more interesting because now that we have a device driver and we have the notion of flows, well, I can now define a TCP stack. And the TCP stack here just needs some idea of what an IPv4 device is, the underlying connection, and then it needs some notion of a flow and some notion of a buffer. And because OCaml supports destructive substitution, we can just very elegantly just say include a device so that this TCP stack is in fact a device, but let it inherit the ID type of the IPv4 stack where it can connect it, and also just include the flow interface. So at this point, we have everything we need to describe a TCP stack. The nice thing is that you can compose these things together, avoiding the diamond problem, because we can destructively substitute the notion of I/O within this one interface to force them to be equivalent with the notion of I/O in device as well. We can also use this to build some really complicated, subtle interfaces. So anyone that follows the heartbleed problem will definitely want to go to Hannes' talk tomorrow in the OCaml workshop, where he's been re-implementing TLS and OCaml in Mirage. But we've had to build some very, very carefully thought through devices such as the entropy device, which gathers entropy from the environment. And this is all done through higher order functions and so on. But the actual models that we've ended up with are relatively small amounts of OCaml, but they just exploit all of the features we often take for granted, such as higher order functions to do handlers and so on. And they've just made life significantly simpler than using C for this sort of kind of low-level system stuff. After this, everything I've shown you so far is very, very abstract. So in Mirage, we very quickly wanted to build these types that are very dependency-free, but then we quickly specialize them into real libraries. For example, there's two concurrently monadically threaded I/O libraries in OCaml that are popular, LWT and async from Jane Street. We've been using LWT because we've been using it before async was released. And we also have a buffer that can deal with buffers with zero-copy semantics, and that's known as C-struct. So the nice thing is we can just take the abstract types, and then we can just substitute in concrete and more succinct implementations, but still keep the original, more abstract types for the purposes of just keeping ourselves as abstract as possible. So those are module types. If you go to the source code, you can go to Open Mirage, and there's a single file. That's really all that Mirage is for Mirage types. It's a single file that describes the essence of all these module types that everything has to conform to. So to actually implement these, everything else used in Mirage is a functor across these set of module types. Now notice that these module types are not large and monolithic like a normal operating system. These functors only have to satisfy the module type of the particular bit of functionality that they care about, and therefore they're abstracted across all of the rest of the OS stack, and therefore can be essentially, you can choose exactly which bits of OS you want to pull in as a dependency. The implementations are extremely flexible. So I just bought some Sonos speakers, and it turns out to use Mirage to control it for my home speakers, I need to do HTTP over UPnP over UDP. This is some nonsense made up protocol from the speaker manufacturer, but luckily with a bit of functors and a bit of application, I managed to get the co-HTTP library talking to UDP, talking over UPnP, and I can actually play music at home again. In a type-safe way, but it's doing this in a normal operating system does require a lot of messing around with abstraction boundaries and so on. And linking to a UDP stack from Linux is just always a little bit painful, so we don't have to worry about that. And also, we have lots and lots of different implementations of module signatures that work into Unix and Zen and so on. So how does it work? So a Mirage component is pretty straightforward. It's like normal code, except it's parameterized by a functor. And so this is what the website that I'm serving this to you looks like right now. It's just like a normal website. You have an entry point that takes in some devices, and the only real difference is the top line. You've parameterized the main function across a notion of a console, a key value read-only store, and an HTTP server, and the rest is just normal camel code. So our goal with this functor is that I want to run it into Unix normally, and so in this case, my little HTTP application at the bottom there has a module dependency graph that satisfies it. That is the HTTP library using Unix, using TCP, and then eventually depending on the Unix module itself, which brings in a huge kernel. But very rapidly, though, I want to start slicing away Unix with surgical precision and start getting rid of all of my dependencies in this big operating system. So the first thing I can say is, let me just get rid of the network stack. So I can replace my HTTP library, my Unix library, with one that uses user space networking in Unix to just use Ethernet. And then suddenly I've sliced away about 2 to 3 million lines of code, and I'm receiving packets in Unix into my OCaml network stack. And then once I'm satisfied that all of that works, I can slice away the rest of Unix and replace this entire notion of network interfaces with Zen device drivers, also written in ML. So this way, I've broken up my problem. I've got a complicated systems problem, and I can just first of all write my web page, which is the hardest bit of the whole lot, just getting HTML and stuff working. And then afterwards, you can trivially put in device drivers and so on, and test them independently. So, so we have this code that's parameterized by functors, and then we also have this collection of libraries where the functors are fully or partially applied, suitable for interactive use. So a number of these Mirage libraries are also just usable normally from a top level without having to use functors, because we just provide pre-applied versions on LWT Unix, for example. And so it's quite nice to be able to interactively play with them in Unix and then retarget the same logic into an operating system context. There's a bit of bad news, unfortunately. These functors are very, very heavyweight, and we need to apply them in some concrete combination. So I've told you that all of the possibilities, but obviously with this many deployment mechanisms, you want to automate that as much as possible. And we use metaprogramming to pull this off. So the metaprogramming DSL is actually very simple. It's very similar to dynamic types in normal languages. First of all, we in OCaml, we just define a type alpha type, which represents the type of values representing module types. So just imagine that you have a number of module types such as key value stores, IP, all of the module types I showed you earlier, and we just define a concrete type to represent each one of those. And we have a little at combinator there that lets you compose these together so that I can take two types and construct a functor type that represents an eventual application of a functor. From there, we also just need implementations, so we define a dual type called alpha impl, and this one has an application operator called $, which will take the applications and apply the functor A to the functor B, and various other helper functions to make that easier to use. So in the website I just showed you, we can very rapidly drop into the host language. So I can drop into normal OCaml, and I'd say, well, I want to choose my network stack based on an environment variable called net. I will then have some other logic to pick DHCP and so on. And then I can eventually pick a network stack from all of the various combinations. I can say, I want a direct network stack in OCaml with DHCP, I want to use a Unix socket stack, and then so on and so forth. But the end result of all of that in the DSL is a stack, which when given a console implementation will give me some concrete module that represents a network stack. And then similarly, after that, we can start applying it. So this is the key use of the DSL. I can construct a server. A conduit is an abstract network channel. That server will result in an HTTP server. And then notice the two key lines, which is the main function here represents the set of module types for the main application. And then when we actually put in concrete implementations here. So I'm saying, given the existence of this set of functors, give it a default console, but it could also give it some logging console, a concrete file system, and a concrete server, and then everything is kind of glued together. All of this works through code generation. So the application code for this it's very, very simple to see how it all corresponds. So here we have the type of a console or key value store, and here we have the associated module types. So you can see there's a nice correspondence. On Unix, the code that's generated is a bunch of functor applications that are quite simple, because we just say that my network stack is a kernel stack, and then just propagate that through all the way to form an HTTP socket. Not complicated. It gets much more complicated in Zen when to construct a socket stack, you don't really have sockets, so therefore you have to apply a ton of functors from various components that form a network stack. So in this case, we've taken an Ethernet device, we've made an IP and UDP. So we made an IP device out of that. We've then made UDP and TCP out of that. But you can see from the TCP device that TCP depends on more things because it's more complicated. TCP needs a source of entropy and a source of time for timeouts. And then finally, we've constructed the TCP IP stack. And then the whole thing is passed on the conduit. But everything satisfies the Mirage module type. So there's a nice correspondence, and everything actually type checks and works. And this is the key to giving us all the flexibility we need to assemble our operating systems. So remember, initially I told you we want to do all these 4 things. Well, if you check out the Mirage website, it gives you all of the well-typed code you need to hang yourself in the Unix tradition. You can, in the host language, manipulate these types of modules very easily and then apply them. But an application error in the EDSL will catch all of the functor application errors. So you'll never get an error that is an untyped functor application that will fail to type check. And the reason this matters so much, the reason this EDSL is important, is if you've ever seen an error from a significant use of modules and functors, you'll often just get megabytes of stuff dumped into your console, and they normally come running to Leo or Jeremy and me for help. So with an EDSL, error messages are significantly simpler. It just tells you your network is not a block device. It doesn't tell you these 2 massive signatures do not meet. So generally, leveraging the host language error messages are better than modular error messages. And we also just have, we can use all the full luxury of the host language, which is optional arguments, to just make it easier and more fun to work with configuration and policies and so on. Anyone can extend this EDSL. So the nice thing is that if new devices are coming along, it's very, very straightforward to just say, well, for example, I've got a source of entropy. All I have to do to define a notion of entropy in Mirage or any other new device driver is just define an abstract type corresponding to the module type signature. So if there's a network or TCP/v4, I just define a new type of type, TYP that is, not TYP. And then you just have to define some mechanism to output the application of the module. So in this case, we have a module type called configurable, which just tells it how to initialize and what module applications are required to pull that off. So if anyone has played with dynamic types, this is actually very, very similar. Dynamics represent a pair between some value and a value that represents the type of that value. In this case, we've done the same thing except with modules. So we've said that our impl represents a triple of its type, a configurable that can actually apply that, and a construction function which represents some mechanism of actually storing its state in the resulting system. Now, GADTs in the EDSL ensure that an impl cannot be applied to a type that does not admit it. So the resulting functor applications are always sound. So by building the EDSL to express the dependencies between all of our signatures, it just becomes quite easy to ensure that by evaluating this EDSL, all of the applications in our operating system are actually pretty sound. So the summary of that is that we've built these applications that are parameterized modules over the dependencies. We've separated operating system functionality into fairly modular chunks. And one of the key contributions of Mirage as an artifact is to provide a vast library of module types that provide all of the things you need to do to build real operating system components. That's actually it's proven to be very successful because as we get real users building these into real systems, they tend to want to freeze one copy of the module types. For example, a version representing some set of functionality, and then they can just ensure that they only select from libraries that implement that particular signature. Whereas, of course, we're always hacking and evolving it, and we can always just select the bleeding edge set of module types, and then only select from implementations that select that implement that new revision, and we do it nominally by revving the names of module types to version 1 to version 2 and so on. The metaprogramming we use to manipulate these modules is quite crude. While the DSL is quite good at protecting us from bad values, we make sure we just output code right now through printing strings. So it would be lovely in the future to be able to use MetaCaml or some kind of a macro system to actually elaborate an expansion in a more principled way without actually having to output concrete strings or ASTs we chose to use CAML for in the future. On the other hand, the approach of staging instead of embedding a more complex module system in the host language, I think has been quite successful. Because once we're done with the code generation, we eliminate all traces of this EDSL and all of the host policies about what configuration mechanisms we want. And the end result, when you're debugging a kernel running in Zen, running in some data center with a billion virtual machines, you want the result running to be as simple as possible. So eliminating all of these functor applications and so on into one concrete thing that you can then debug is much easier in runtime if you're stuck in a GDB prom, for example. Whereas if you've got all of the logic stuck into one thing, you've not actually really shrunk any of the complexity. So we like the approach of just building a configuration file that is then evaluated to build an executable kernel. And people have been building lots and lots of libraries of different policies based on where they want to deploy things. So some chap came along recently, in fact two, Gabor Pali came along and built a FreeBSD kernel module version of this. So instead of just going to Zen and to Unix, you can also load kernel modules now. And Andy Ray is building a JavaScript version as well for reasons that are as yet unrevealed. But I'm sure he's got a good reason to compile an operating system to JavaScript. But it really doesn't impact any of the core libraries because the TCP stack, for example, is just pure CAML parameterized over a network stack. That compiles just fine into JavaScript, where the problems are normally around C bindings and other kind of hooks into the operating system. Our hooks are just functors, so you can just replace those with JavaScript simulations or raw sockets or whatever they are in JavaScript these days to pull that off. So we've got a growing body of code that's quite nice at expressing the essence of bits of operating systems and can be retargeted into all of the backends that CAML supports, which is quite a few. We do also have a growing open source community, which shouldn't surprise me. It always does surprise me that other people care about an experimental operating system written in a fairly obscure functional language. But we've had a ton of really, really smart, motivated people join us to actually make this into a real operating system. And OpenMirage is part of the Linux incubator project system as part of Zen. And so we're actually hosted outside of Cambridge now, and there's a governance model, and we're very welcoming to new people that want to contribute new code and actually help some of the other users who are building real deployments in Mirage turn that into reality. We always need people who can implement protocol stacks or just want to have some fun with a particular protocol or deployment. And a number of them have actually written blog posts about their experiences, and you can find them all on openmirage.org, along with a growing and mostly accurate set of documentation that will get you started with the Zen backends and so on. So if you're also interested in kernel hacking, it's a good way to become a kernel hacker without ever writing a line of kernel code, because the resulting binaries are standalone kernels, and you never have to leave the comfort of ML to get into that world, which is a nice way to enter an otherwise hostile environment for many people. So that was a bit of a whirlwind tour of the metaprogramming. Are there any questions? Hello, Ron.
So you have this little EDSL for expressing something. I didn't see sharing constraints or anything like that. And I'm curious in general how you handle sharing. For example, let's say you have like a big library full of modules, and you want them all to share, say, the same TCP IDs.
Yeah.
How do people write everything as a functor, and just sort of like stage those together and in order, and how do you know the order?
Yeah, this has come up a few times. So yeah, we do indeed do exactly that. We tend to encapsulate everything within a tree of applications, so we don't have to deal a lot with sharing. Now, we have talked about trying to pull out various components into a slightly higher level of application, so you can do limited sharing. So one example is that I want to build a DNS resolver, and the DNS resolver needs a TCP stack to just do DNS resolution. Now, the problem is, in this case, you sometimes want to separate the stack that's doing DNS resolution from the stack that is actually making the HTTP requests. So you don't want to enforce sharing. So what we haven't done yet is to put a notion of sharing directly into the application language. But to some extent, this is a matter of you could do this in the host language in theory by helping, by controlling when you do the application.
Also, have you taken any inspiration from SQL's Operation Manager? Or doing some of these things kind of issues?
What is the XML compilation manager? Someone tell me.
It's a tool for managing, XML compilation.
That's amazing. It doesn't. All right.
And so it's usually called CM.
Right.
And it does dependency analysis. So it's unlike, say, Milton's B, which is also a compilation manager. It automatically figures out which order modules to compile them, and it also provides namespace management, and so it's that extra level of module system that you need in order to be able to deal with signatures in a, to be able to have like libraries that have internal signatures that aren't going to conflict with signatures elsewhere.
Oh, that's fascinating. No, I haven't. The closest we've done is, well, Tom Amelie has built the OPAM package manager, which is working in the level of compilation units. And so we did for a while select the set of libraries that we would eventually compile based on OPAM constraints. So there's a SAS over band scenes that would pull that off. But at the local level, we don't. Although the direction we're going in is more interactive dialogues and so on to help people, like Linux kernel management and so on. The actual module selection has not been a huge problem so far. But Tom, do you have any flavor? Well, it's interesting. I didn't even know it existed, so I will look at that and be inspired in the future. Please.
So you had FoxNet on your slides briefly, but you didn't mention it, and I'm curious. So I obviously wasn't part of it, but FoxNet I don't think we could have characterized as the kind of success that you've seen here. So what is it that's different that makes this work when FoxNet didn't?
So first of all, I think FoxNet was a success because it directly inspired me to do this work. So that's like, why isn't FoxNet a success? We should sort this out. And it's awful. And there's a bunch of really good systems that seem to have almost got it. Well, one of the key things is that I was part of the team that built Zen. So having a virtual hypervisor platform that and one that you understand is very important because typically building an operating system is just a really laborious task of supporting device drivers. Now we just have to support Zen and its quirks. It's not a large number of platforms. The second thing is that having the OS construction around the TCP stack is really useful because the TCP stack just by itself is of limited utility. Whereas with this, we actually have a story for serving protocols, and TCP is just a bit of middleware that actually enables us to do RFC compliant communications. So FoxNet taught me a lot about how to do the module structure. In fact, the first version of Mirage was functorized. I didn't really understand functors then. We unfunctorized it. That was a mistake. Then we went back after understanding functors. So because the SML model didn't have destructive substitution, so it just made it quite hard and awkward to use modules at scale in the style that we were using it in. And a quick conversation with Jane Street this morning also revealed that there was a number of awkward workarounds in the Jane Street code base for the same diamond dependency problem. So it made having a good hypervisor platform and just finishing the project as well, right? After the job of working with the PL side of things.
One more question, maybe?
So I'm just curious what you miss in the modules. For example, mixing composition,
the main thing I'd love to have a notion of backtracing because when you do a very large and complicated application, you don't know why some type propagations have not propagated and so on. So having an interactive mode where you can see all the propagations, all the notions of type loops, and being able to debug where the bug happened. So the biggest problem in the module system is not really a bug, it's just that it doesn't have the richness of debugging facilities that you do have in a normal host language. And when we're using it at this scale, so there's often over 100 module applications in a typical system. If you get a bug, if there's a bug in the EDSL, it's just very, very hard to debug. Beyond that, an easier way to do sharing is high on the list. So that's what we're going to do next. Because if we do want to share whole components like stacks, we'll either have to lift them out of the EDSL or do something very, very ugly looking with sharing modules. Tom is not very happy at me for suggesting this, but we will know quite soon. So I anticipate another 4 years we'll have an experience report telling you how we have to hack the kernel module system with implicits and macros to pull that off. But none so far.
Okay, let's thank the speaker again.